Hello, everyone. Welcome to the module on linear regression. So, as usual, all of the necessary files are on our BCI Workshops GitHub repo. And in this video, we're going to go over the linear regression on housing data notebook in detail. And linear regression will be important for us for BCIs, for machine learning when we want to train a model, and it follows a linear regression sort of pattern. There are other types of regressions as well as logistic regression. There will be a separate video on that. But for now, let's go ahead and go through this housing data tutorial. So the first thing that we do is we're going to import all the necessary modules for this. So the takeaway ones are Pandas, NumPy, scikit-learn, matplotlib. Those are usually universal ones that we'll see everywhere, and we're probably going to use those in practice as well. So the next cell takes in, uses the Pandas library to read in the training CSV file. And if we want to look at what this file kind of looks like, it basically has a bunch of features of certain houses. So there's like crime, which is like the crime rate, the age, how long it's been there, tax prices you have to pay, stuff like that. So all of the attributes from crime to LSTAT are all of our feature variables, and MED V, which is the median value of the home, is going to be our target variable, which is, so essentially in this model, we want to train the machine to predict the median value price based off of all of the other features that we would feed into it for any given house. Okay, so that's what the CSV file kind of looks like for context. And what we're going to do is we're going to create just a couple of variables of our untouched data. So again, we're going to call CSV and just basically essentially make a copy of data set, because we're going to modify data set. We want to just keep a copy of the original, as well as all of the columns of our data set. Get numeric data will basically get all of the columns and store it into a list. So I already kind of went over what the data looks like, but we just used dot head to get the first 5 rows so we could get a better idea of it. And again, the cell over here, these are just also variables that we can use as handy, getting the number of rows and columns as well from, and we got this shape. So the shape function will give you like information about the data set variable, the pandas variable, and give you like the number of rows and columns, just so that we can explore the data using some quick functions. Okay. The next thing, now that we have the data stored into variables, we're going to pre-process the data. The describe thing returns like the mean, the max, the standard deviation, etc. In the series object or in the pandas object, either or. So we're going to go ahead and get the mean for all of these attributes. And again, we could replace this with, as you see later on, we have the standard deviation that we stored in a variable, and all of the different percentiles we've also stored in variables. These are going to be useful when we go ahead and remove the outliers while pre-processing. And other variables that we got was all of the titles of each of the feature and target variables, right? Just storing that in as well when we create heat maps and stuff, so that we have context as to what all of the data that we stored into variables have corresponded to. So now let's go into finding our outliers. So if we recall, there are 2 ways to find outliers. The way that we're going to do it right now is via z-score. So in a data set, we can call outliers that have a z-score greater than 3 or less than -3 as like outliers of a data set. And again, this, you can be like more picky about this, but 3 is kind of more of a universal sort of thing, assuming it follows normal distribution, stuff like that from stats, right? We all remember that. So we're going to go with less than -3 or greater than 3 are outliers. So I created a quick function called find outlier. I'm sure there are other ways that you can remove outliers, but I just found this way to be straightforward yet customizable. If you wanted to change the z-score to get a more narrow range of values, you can do that through, you know, data investigation, see what is like the most ideal z-score value for you. So that's why I did it via like a traditional function sort of way, but I'm sure there are other like libraries that you can use that do the outlier removing for you. So yeah, I mean, we have an empty array for outliers that will store everything from the data set, and we iterate through each value in the data set. So what's going to be stored in our data set variable are going to be our z-score values, okay? We're going to calculate those later on in here, but in this function, we pass in the z-scores, and it's simple. If it's, you know, the absolute value is greater than 3, you like append the outlier value to this function, and then we return it at the end. So to calculate the z-scores, if you remember, to calculate z-score, you do the value minus the mean divided by the standard deviation. So again, we're going to go through every single value in the columns, and then we're going to go through every value within that column. So that's what this nested for loop does. And we're appending the z-score values, okay? And when we print it out, we can see all of the wonderful z-score values. It is a very, very long list. So just, you know, we got the point. There are a bunch of z-score values. And then we're going to run the function that we made. And as you can see here, all of these z-score values are greater than 3. Let's find one that's less than -3. There we go. So that's just confirmation that, you know, this worked well. So the other way that we can like replace outliers is through the interquartile range. So if you remember, the interquartile range is the 75th percentile minus the 25th percentile. So we went ahead and calculated this interquartile range. Just wanted to reiterate, this is the z-score method is one of the ways to, you know, remove your outliers. And this is like an alternate way. So yeah, I just wanted to reiterate, these are not connected with each other. So going back to IQ, like replacing them via IQR, we went ahead and got the lower bounds and the upper bounds by subtracting 1.5 times the IQR from the 25th percentile and adding it to the 75th percentile. If you remember stats, this is like 1.5 is again kind of like that magic number. So again, I'm making this a pretty like standard protocol, assuming that the data is pretty normally distributed. And then I made a variable A, and what this does is it stores all of the values per each column, okay? And this nan percentile will essentially store all of the percentiles per column of whatever n percentile you pass. So P98 is going to store the 98th percentile for each column, and P2 is storing the 2nd percentile for each column. Okay. And then we're going to go ahead and go through each element within the columns. And if the element is less than the lower bound that we calculated, we're going to go ahead and replace that with the 2nd percentile and the 98th percentile. So we're basically removing like extreme outliers at the ends with like these, we're removing like the lower bound and upper bound values with the 2nd and 98th percentiles. So we overwrote the data set. So right now, whatever we're going to, like the data that got pre-processed via removing outliers is through the interquartile range. You might have noticed that I didn't actually implement replacing the z-score values or removing them. You could do either. Again, it depends. The experimentation is up to you. But yeah, with the z-score values, you would, I would probably just remove all of the values that correspond to these z-scores. And this cell, this is a typo. I don't know why it says age, but essentially here we're using the distplot function to go ahead and plot the medium value house variable with respect to density. So this is like a density plot. As you can see, it's fairly normal, slightly skewed to the right, but it looks pretty good. So that's just kind of confirmation that we can use this as our target variable because of the like regulatory curvature of the data. If some features don't matter, for example, let's say that we see not a lot of correlation between age and the median value. I'm sure there is a correlation, but let's say there wasn't, then we would know to exclude age as a feature value for the median because it doesn't affect it. This will make our model a lot faster when running because it's one less feature to worry about, as well as potentially more accurate too, because some of these things just may be fluff and distract the model from giving like the most accurate results. So to look at the relations between these, we're going to go ahead and generate a heat map. So a heat map is actually pretty nicely visual. It has this gradient of correlatory variables. So the more like light it is, the less correlation there is, and the darker black it is, it's a correlation of 1, and like the more red it is, it has more of a negative correlation. So obviously, if you see in this diagonal, everything has a correlation of 1. Why? Because here you're comparing median value with median value. So obviously there will be a 1-to-1 correlation. But so kind of ignore this. Let's look at what's like gray. So if you see here, tax and RAID, for example, they have a pretty decent correlation of 0.8. But what we want to focus on is because our target variable is median value, we're going to go ahead and look at that. So here we can see that LSTAT seems pretty, it seems pretty strongly correlated in the sense that, you know, it's maybe like negative 0.7 negative correlation. This black parameter, not so much. It maybe has like 0.3, so on and so forth. So you can pick and choose the values, the features that you think would be relevant for your model after this point. Another way to look at this is through a pair plot. And again, this does the same thing as the heat map. It puts all the parameters on both the X and Y axes and it compares them. So to draw parallels, let's look at median value and LSTAT. I would be expecting a sort of negative correlation. So that's this plot over here, and you can see it does look pretty negative, right? So these are just two ways to analyze your data points. It's really fun. I could do this all day if I wanted to. But for the sake of this tutorial, we're just going to go ahead and put all of the features in. Of course, removing some, as I mentioned before, would probably actually result in a better accuracy. But we're just going to go ahead and put all of the features in the X and our target variable in the Y. And then we're going to use this function train test split. and pass in the X and Y values. And what this does is this splits the data into training and testing. Size of 0.4. So we want to train 60% of it and test 40% of it in this case. And then I also made a function called clean data set. This will pretty much remove all of the fluff values that are in there, because when we run the model, the data has to be pretty much pristine. It has to remove all these extraneous values. Otherwise, the compiler will complain that like, I don't know what this NA thing is, or uneven number of rows and columns, etc. So this is going to be really handy for us. Then we're going to convert the train and test objects that used to be series into data frame objects, so that we can run the linear regression fit thing. I cleaned the data set for all the values. And then here I made a linear regression object. Again, so linear regression itself is an object and it has a bunch of built-in functions into it. So you could go ahead and look into the documentation if there's something interesting there. And then finally, we go ahead and run this linear regression fit model with our X train and Y train, with the pre-processed and cleaned values. And finally, we go ahead and plot it, and we can see what our predicted Y value will look like through Y test, and the correlation looks positive. So yeah.